All right, so a couple points of business. Hopefully you were able to find the PDF of the notes we took on the website, along with the link to this stuff on YouTube. That's helpful. I haven't updated any of the type notes, but we're still kind of, the type notes are still kind of quite far ahead of where we are in class. We started last class talking about introducing fundamental dimensions. I mentioned that this first topic, I think, is pretty familiar for most people. Oftentimes it's familiar because it's covered pretty well in the fluid mechanics course at an undergraduate level. I'm going to try to give an example from solid mechanics today, and then also introduce kind of a slightly more complicated approach. There was one question that was raised about the fundamental dimensions last class that I didn't have an answer to, that I wanted to address. Someone had said, what about radiation as a fundamental dimension? And so I kind of did some digging, and from what I gathered, radiation is really quantified with its radioactivity, which is the kind of number of neutrons that are decaying per second. So the units, I believe, for radioactivity are 1/time, or I think you could probably think about it in terms of like moles per time. I think the moles of some of the actual number of neutrons over the decay. And so for the question about radioactivity, I think that can be lumped into the dimensions that we outlined here. All right, so starting today, I kind of wanted to just quickly review what we did towards the end of last class, because I sped through it a little bit. I sped through it because I think it's familiar, but this will kind of motivate another problem that I don't think you've seen before, and then we'll get into like a slightly more complicated problem that kind of really shows the more powerful side of dimensional analysis. So just to recall what we did last class, is we used just the dimensions of the problem to calculate what the drag force on a sphere would be. And we said, well, it probably depends on the radius of the sphere, the velocity, and it's moving, the density of the fluid, the viscosity of the fluid, and we arrived at something that looked like this. And you'll get different forms of this equation. So what I mean by that is these terms here might be different if you solved for instance, we kept D unknown here. We had kept B or C or A unknown, you would get slightly different form here. But the end result would be that if you took the drag force and divided it by these dimensional terms over here, you would have a dimensionless number on the left-hand side, and then you would have some function on the right-hand side, f of pi, which we don't know. And f of pi is something that you can measure experimentally. And we talked a little bit about this concept of physical similarity, this idea that the drag force depends on these physical parameters, and then it also depends on some unknown function, f of pi, as we vary pi. And I talked about how this presents a nice opportunity to create scale models, just like how we're used to the concept of similarity, geometric similarity in similar triangles. As you kind of scale up from a small triangle to a larger triangle, you end up with similar angles. The concept of physical similarity is really important, and the point I want to make is kind of twofold. One is, if you end up with a scaling like this, you can set up a scale model where you do something like this, and you say, okay, well, I'm gonna, in my experimental setup, set my dimensionless product. So if you look over here, it's mu, r, v, and rho. So that's my dimensionless ratio. As long as I keep my dimensionless ratio the same, I can kind of vary certain parameters in the problem. It might be hard to vary experimentally. So for instance, in this problem, as long as you know your goal is to keep pi the same, you might be interested in figuring out what happens or how f depends on pi as you make the radius of your sphere bigger. And you might be able to not make an experimental setup that allows you to test the radius so big. So you keep this pi parameter, the ratio here, the same, and that'll allow you to tell you what's going to happen as you scale up or down the radius of your problem, the radius of your sphere. The second point, which is a little bit more subtle and a little bit more instructive, which is that if you see some sort of physical similarity in your problem, that usually should motivate you to go and look for a scaling. So let me give you an example of what I mean by that. So here is a problem. Here's a problem in brittle fracture. And I'll make this, you can see that just 1 second. So here's a problem in brittle fracture. So this thing here, this is just a schematic of it. So this kind of rectangle here is a piece of glass, fused silica. And right up here, you can kind of see a black little parallelogram of sorts, which is a punch. So it's just a very sharp, small punch that is being pressed into this fused silica. And what the experimentalists observed is they're trying to understand brittle fracture. What they observed with their experiments was that as you applied more and more load to this glass, you would end up creating a conical fracture. So this is a cross section, so it looks like almost like a triangle. You can imagine this thing is axisymmetric, so it's kind of like, so it's a cone. So here you can see that at one force, your cone has a base width of d1, and that's occurring at a force of p1. As you press a little bit harder, the shape remains the same. It just continues to get bigger. And so the question is, okay, well, how does that shape, or how does the largest dimension of that shape vary with the load you're applying? This to me is an important and instructive example, because if you're in the lab and you're doing some experiments and you see something where, oh, as I increase this parameter, I'm seeing the same shape. Maybe it's a vortex, and this vortex is looking like it's getting bigger. It's the same shape, but it might be scaling it up or down. But the size or the similarity of the shape that you're looking at kind of remains the same. That should kind of tell you that there is likely some sort of similarity or scaling that can be done to predict what that shape is. There's something underlying that physical phenomenon that is kind of keeping that shape self-similar. And so here's the data, and this is the data of D, which is that base width as a function of force. This is a load-controlled experiment, so they're just applying, imagine this is meaning like they're applying more and more force on top of it, as opposed to controlling displacement where you're fixing how far you're pushing into it. So what do we do here? So how do we come up with or construct the scaling to try to predict this behavior that we're seeing? So fracture falls under elasticity theory, and elasticity theory is a little bit tricky because oftentimes you're taught linear elasticity. It's usually the entry that you're given. And linear elasticity, it's a linear system of equations, unlike navigator Stokes, which has nonlinear terms in there. The linearized form of elastic behavior of material predicts that you can kind of increase the load indefinitely, and you'll just indefinitely increase the displacement system, which we know is not true. We know that if you bend something too much, it'll break. If you pull on something too much, it'll break. And so it seems like that model would be insufficient to be able to capture fracture. But on the other side, we also know that there are lots of materials that when you break them, you can kind of piece them back together, and it looks like the same object. You break a coffee mug, most of the pieces can just be kind of stitched back together, and it looks like a coffee mug. That's what's called brittle fracture. It means this thing broke without plastically deforming much first. Okay, so that seems to say the opposite, which is, well, if I didn't see any plastic deformation, that to me suggests that a linear elastic model should do pretty well. Like I haven't really had that large of strains. Strains are pretty small if the structure kind of is able to go back together. So we should be able to hopefully learn something using a linear theory. And it turns out we can. We just have to think about how to account for the nonlinearity appropriately. So what's the nonlinearity in a fracture problem? Well, the nonlinearity in a fracture problem is that usually you think of elasticity is going to give you a set of kind of boundary value problems. You have some set of equations, you have some known boundaries in which you're going to apply forces or displacements, and then you're going to solve to see if you can either determine what the load is in the, or the stress is in the material, or what the displacement of the structure is, depending on what you're interested in. The problem is that in fracture problems, there exists kind of more boundaries than we're thinking of. So what do I mean by that? What I mean is, if you take a material and you want to know when it's going to break, every material you're going to find, no matter how perfect, is going to have some defects or imperfections on a micro scale. And as you're kind of pulling on this object, those little micro cracks or nano cracks are going to be growing in length. And that's the non-linearity. You now have this kind of new boundary that you weren't really thinking about inside the material that's growing. And this is what leads to this material fracturing. And so what's needed is a way to account for this creation of surface area within the material. And so one of the parameters, a material property that people will talk about is the energy release rate. So, oops. So this is a measure of essentially how much energy does it take to create a unit of surface area within the material. So this is energy per area. This is related to another concept that we're going to use, what's known as the stress intensity factor. I like to think about the stress intensity factor as a way to kind of quantify stuff that we know intuitively. For instance, take a rubber band, put a notch in that rubber band, just like a tiny little defect in it, and then stretch that rubber band. You know that that rubber band is going to break right where that defect is. That little defect there is going to propagate through the material and cause this thing to fracture. And physically what's happening is that you're applying some amount of stress to this material by pulling on it, but that stress is going to be amplified near this crack. And so it turns out that you can write down your stress intensity factor. It's usually denoted with a capital K. And the stress intensity factor will scale as the average stress in the material, sigma. So this is kind of like the force per area that you're applying to this thing. And then times the square root of the distance away from the crack. So let me draw this out schematically for you. So first I'll write out what these things are. So this allows you to take a material that has a crack in it, apply some average uniform stress at one surface or both surfaces, top and bottom. And what this stress intensity factor is saying is that the average stress in this sample is going to be the average stress kind of amplified by how far you are away. So the closer you get to, say, here, the higher the stress is going to be. So larger stress, you can go kind of rainbow, less large stress, and so on and so forth. Which kind of matches our intuition. The stress should be larger near the crack tip. You can go into detail to figure out kind of where this comes from and how the stress intensity factors depends on how you're loading it. But for right now, we're not going to worry too much about that. Just conceptually, just we need to know that the stress in the material is going to be amplified near a crack tip. Okay, so When I mentioned earlier that this experiment was load controlled, which means that we're applying a force P. Whenever we have a load controlled experiment in elasticity, that we don't need to account for the elastic modulus. The stress is independent of the elastic modulus. If you're doing a displacement control test, it's the other way around. You need to account for the elastic modulus. So what do we have here? We can use our dimensional analysis to figure out what's going on. So we have in our problem, we want to know, how does this crack grow as we apply more and more load? So we have kind of our crack dimension, d, which is going to be some function of, let's see here. It's going to depend on our load P, our stress intensity factor K. The material property that we do have to account for is the Poisson ratio. If anyone knows anything about elasticity, you know that the Poisson ratio is dimensionless, so it's not going to really help us in our dimensional analysis. We can pretty quickly apply the same approach we did before to solve this problem, which is to say that, okay, well, what are the units of P? So the units of P are force, and the units of force are mass times acceleration, so m times length times squared. And then K is going to be let's see if that's force or stress. Oh yeah, no, that's fine. K is going to be force per area times the square root of length, right? So this is stress, and this is the square root of length. And so this should be force mass length time to the minus 2 times length to the 1/2 over length squared. So it's kind of a mess, a little bit of algebra, not too bad. We can find that this should be equal to mass length times minus 2 divided by length to the 3/2. That is really hard to read. Let's see if I can make that smaller. So balancing these two, so putting all this together, there's really only two parameters. There's this one and this one. The forces are going to cancel out pretty nicely, and our scaling should suggest that the width of this crack should scale as the applied load over the stress intensity factor to the 2/3. And then we're left with some unknown function. We'll call that unknown function, I don't know, let's call it phi. Unknown function of our Poisson ratio. I'm rushing through this quickly because I wanted to get to two other points. The purpose of this, you could do this really quickly yourself. So the dimensional analysis tools we had, if I kind of tell you the important parameters, no problem. It's just a system of equations. This should be pretty straightforward to solve. But I want to get to a couple of different points. One, you see this scaling emerging in your data, or more importantly, you see this kind of physical phenomenon propagating in your data. That should tell you there should be some sort of scaling at the heart of this. How do we find it? We identify what the important parameters are, and we just balance the dimensions. And you probably can't tell, but this thing here, oops, is in fact going up at 2, 3. This is a log plot, so the slope of that thing should be about 2/3. So that's the first thing. So this is a kind of important parameter, and just a kind of sanity check to give you an example that's not from fluid mechanics that you haven't seen before. But a couple of points are, observing this should tell you there's a scaling that you should be looking for in your problem. And then another important point is that we obviously neglected some stuff. So what did we neglect? I didn't say anything about this dimension, and I didn't say anything about this dimension. Can anyone guess why? Or let me put it a different way. Can anyone guess when they would expect this scaling to be valid?
Like the extreme case?
Yeah, so would you expect it to be valid in the extreme case? Well, what does the extreme case mean?
Like when the D becomes really large.
Yeah, exactly. So what I've done here is essentially neglect when the system is really small and when the system is really large. If anyone's ever taken I think this is usually covered in like a fluid mechanics course where they talk about G.I. Taylor's scaling, predicting the amount of energy in an atomic bomb that has gone off. So there's this blast has this blast radius, and that blast radius kind of grows with time. And just by looking at the blast radius, Taylor was able to predict how much energy was in the atomic bomb. One of the important things and the assumptions used in that was to be looking at it in this kind of steady state when the blast front is propagating, not too close to when it has exploded, and not to the point where it's so far away that it's really dissipated. It's really in this kind of steady state phenomenon that we see this scaling emerge. This is true in a lot of problems that utilize scaling. I mentioned earlier about vortex shedding. Vortex shedding is another nice example. The vortex has a self-similar pattern to it as it grows, but that self-similar pattern doesn't appear instantaneously after the vortex is shed, and eventually it loses that kind of connectivity. And the same thing is true here. And so the point I wanted to bring up is that this length here, and you should confirm that is a length, this length sets the limits on when something's too big or when something's too small. So what do I mean by that? I mean that this scaling should be valid. Oops, I'll make that smaller. The scaling should be valid as long as the punch diameter, that little d, relative to this length, relative to p over k, is really small. Ooh, that's not less than sign. And when the largest diameter of the system actually, should that be, this must be a delta, sorry. Can't read my own handwriting. Capital delta, which is this thing here. Relative to p over k, the 2/3, is really large. This is really, really common. This concept that you have a scaling emerging in your data. You can use something like dimensional analysis or maybe something a little bit more sophisticated to find that scaling law. And that scaling is only going to be valid in some intermediate regime. One of the books I recommended was by an author called Baron Black, who's really pioneered a lot of the kind of foundational theory behind these scaling laws and how to use dimensional analysis to solve problems. He refers to this as what's called intermediate asymptotics. essentially, once you're kind of far from that initial point, but not too far away where you're at the other extreme, you're in some intermediate regime where you establish some steady state, then your scaling law is typically going to be valid in that intermediate asymptotic regime. And so the purpose of this example was to kind of show you something that's not drag on a sphere, but also to kind of highlight that we expect these scaling phenomena to work in some intermediate steady state regime. Now, what that intermediate steady state regime means might not be obvious to you when you're doing it. You might have started the scaling by saying, I've got to include little d, I've got to include capital delta, and then you're going to end up with a bunch of dimensionless parameters. And that's fine. What you should do as the modeler in that situation is say, okay, is there anything I can assume about these? I have a bunch of parameters I don't know. Can I assume any of them are small or any of them are large? And if I can I neglect them, arrive at a really simplified scaling, and then try to understand how what I neglected kind of fits into this definition of this intermediate asymptotics. And, or as we'll find later in this course, how do we kind of build back in? What if we're really interested in what happens in the initial behavior? Well, there's ways we can kind of go back and kind of build back in that, let's see here, this parameter as a small parameter that we can kind of see how it affects the problem. Questions? Does this make sense? I went fast through the scaling derivation. I think you can do that on your own to check. I'll have a homework assignment for you soon so you can kind of practice going through this. But I really wanted to highlight how you can use your experiments to tell you to search for a scaling, and also how you can kind of simplify things by recognizing that these scalings typically emerge in some intermediate regime. Yeah.
Would you say that the idea of the intermediate regime, that if there was some more universal model, those sorts of situations where that intermediate regime isn't valid is because it's approaching a boundary condition, or because just kind of looking at this example, it looks like, okay, if that cone extended to the edges of the glass, then you might be hitting a boundary, and that's why it would fall apart, and then the same thing the other way.
Yeah, that's a great way to think about it. In fluids, you often kind of separate problems when you have kind of flow versus like a boundary layer flow. In solid mechanics, you might, imagine cut a tennis ball in half. It looks like a spherical cap. Flip that dome inside out, and you're going to get a spherical cap, but then you'll have a little flat rim around the edge. I don't know if you can picture that. It'll have like a little, almost like a little hat rim on the edge of it. That's a boundary layer in solid mechanics. That's where you kind of have some behavior in the dome that looks like a spherical cap, and then some behavior right near the edge that doesn't, and you have this deviation. One of the things we'll do in looking at when we start dealing with perturbation methods is talking about how to look for solutions away from the boundaries and look for solutions near the boundaries. And then you can get into more advanced mathematical techniques, which we'll do here, in which you try to match those solutions. You say, well, this behaves this way along the boundary, this behaves this way along the bulk. There's got to be some way where we can match those together and get a continuous function. And so that's what you refer to as matched asymptotics, which you're matching the behavior at the boundary to the behavior in the bulk. In this particular problem, there's two boundaries. There's a boundary at small d and a boundary at large delta. And so you're going to have some intermediate regime, a matched asymptotic regime near the small crack, and a matched asymptotic regime near the large crack. And some of that comes down to identifying what do you need to know about your problem. If you need to know the small regime, the scaling is not going to help you, and so on. So that's a great question, and that's usually where these things emerge. Yeah. Other questions? Nothing? Anything from the remote folks? Hopefully you're all there and can hear me, and I can hear you, hopefully. Let me just make sure there's nothing in the chat. Cool. All right. Should I move on? Is this okay? Okay, cool. All right, so far we've really done some basic algebra to figure out some simple scaling, so we know the relevant dimensions involved. The examples we've given, for the most part, we have intuited what they are, or I've told you, like this matters and that matters. More often than not, or I think what's fairly common is you're going to have some governing equation that you'd like to know a little bit about. And we can apply the same technique here. And the example I'm going to give you is one which is going to take an equation that is difficult to solve and make it easier to solve. And this is relying where'd that go? Come on down. We're going to talk a little bit about similarity variables. So again, building on this idea of physical similarity. And to do so, we're going to look at another problem that I think is probably familiar to you. If you've taken a class on differential equations, or especially a class that involves PDEs, you've undoubtedly encountered the diffusion equation. If you haven't, that's fine. We're gonna solve the diffusion equation differently. And so the problem we're going to be interested in is finding the density of some chemical along a line. So you have some source where you're releasing some initial concentration of some chemical. It's going to propagate in space and time, and eventually reach some steady state equilibrium where it's kind of everywhere in that system. So let me draw what I mean, in case that's not clear. So we can have some variable where we're looking at the concentration. We'll call it concentration U. We're going to start at some kind of initial concentration. We'll call that U naught. This is going to be our x axis. And at time 0, I'll color time 0 with purple. Time 0, all the stuff is here. At time 1, oops, at t equals time 1, you're going to have something that looks a little bit like there's a concentration really right near where this thing was been released, and then it's kind of decaying to some other variable x, or you can call it x1.
Is it like constantly releasing something from the source?
Yeah, imagine like an infinite bath
Oh,
of concentration U naught over here at x0. And so it's basically propagating. I think another way to think of it is like take a really long bar and just stick a hot plate on one side of it, and then you're not really draining the heat from it. Imagine that thing is just so big that it doesn't lose any temperature. If it loses temperature, it's a more complicated problem, but yeah, exactly. Okay, so this is the problem. So this thing should eventually kind of, we can do, we can obviously keep going, and this should kind of look like that at T2. And this problem, I've already told you, is the diffusion problem. This density will satisfy the diffusion equation. What's the diffusion equation? D. Actually, my handwriting is terrible today. All right. The diffusion equation is a partial differential equation where we have the second derivative of concentration in space and the first derivative of concentration in time. To solve this equation, we're going to need two spatial boundary conditions and one initial condition And we already know what those are, so we can say that U at x equals 0 is U naught. Our initial concentration at the origin is whatever we said it was, U naught. U at x equals infinity is 0. So this thing never gets infinitely far away. So these here are your two boundary conditions. I'll call these BC. And you need one initial condition, and that initial condition is that, oh, I did that wrong. Oh no, that's fine. Is that at the concentration at time at the starting point is 0. So U at t is equal to 0 is equal to 0. Just to be clear, if you've taken a class on PDEs, you know how to solve this. You can mount this problem onto a semi-infinite spatial interval and use an integral transform to solve this problem. We're going to do it a different way. And we're going to do it a different way to show you how dimensional analysis and identifying important variables can dramatically simplify the math that you're looking for. This just happens to be one of the 3 straightforward to solve PDEs. But anything more complicated than this, and you're kind of out of luck. And so understanding how to simplify these problems can be a huge step forward. Okay, so this is the equation we need to solve. These are the boundary conditions. I didn't label the initial conditions. Let me do that. This is the initial condition. Let's say you don't know anything about diffusion. You can start by looking at using dimensional analysis to figure out what all the parameters in your problem are. In this problem, if you've done something with diffusion, you kind of know it's a flux. You can probably guess what the units are. But if you don't, that's okay. I'm going to use this as an opportunity. One of the things that always, I think, throws off people when they're first introduced to dimensional analysis is how do you do dimensional analysis when you have derivatives involved? It just kind of looks, what does that mean? But it's actually quite straightforward. So I'm going to just illustrate that over here. And I think as soon as you see it, you'll be like, oh yeah, this is not really, okay. So let's pretend we have something, I'll call it, it's an area, we'll call it A. So this area is a function of X. It's my area A. And we'll just say, for simplicity's sake, the area is X squared. So clearly the units on this thing, if X is a length and this is an area, the units of A are length squared. Now I can look at the derivative of A, so I can say, well, I'm really curious to see how dA dx, and that gives me 2x. Therefore, the units of dA dx. If you want, you could think about this as saying, well, I'm taking a derivative with respect to space, so therefore I'm going to take 1 over length times the units of A. That's fine too. Or you can just look at the derivative and say, well, it's got X, let's go to the units of length. Either way, you get the right answer. And second derivative, so on and so forth. Again, I'm taking 2 spatial derivatives, which means I could, if I want, conceptually think about this as saying, I'll take 1 over length squared times the units of A, and then this thing is dimensionless. If I'm taking integrals, it just goes the other direction. So if I'm taking integrals, I gain a length. If I'm taking integrals with respect to time, I gain a unit of time. And so you can take the units of whatever you started with, multiply that by the length of time. So, so this would be derivative derivatives. And this would be, this way would be equals. Okay, straightforward, not too bad. So come back to what we're doing. We know dimensionally that we should, for this equation to be valid, we know that the dimensions of D times U comma XX, where I'm using this notation. The comma denotes partial derivative. The letters after it denote what I'm taking the partial derivative with respect to. So I'm partial x. This must equal u comma t. It's terrible t. Okay, I can, if I require these all to be the same, and I know that concentration is mass per volume, so I'll write that down because I don't think I actually said it yet. So the units of U are mass per volume. You should be able to quickly go through on your own and confirm that the units of, if we know the units of U, I can apply these derivatives with respect to space and time to figure out what the dimensions of D are. This is really powerful. It's, for this case, it's kind of silly because we probably know that D is the flux, and we've encountered this problem before. And so the units of D are going to be length squared per time, so it's area per second or area per time. But I promise you there will be, there are numerous times when you're looking at some system of equations, there's some parameter that you don't know what it is, or maybe it's defined slightly differently than the way you're used to. This process can be like a real first sanity check to be like, what is this parameter? I had to do it. I was looking at a problem I was going to think about giving you all for a project, and it wrote an equation in a slightly different way, and it introduced this. It was like, here's A. And I was like, what on earth is A? And basically went through this process to figure out, okay, A is so on and so forth. So this, to me, I do this constantly when reading papers, and I also do this constantly when looking at my students' work to see, like, are their equations valid? Are they writing down valid equations? So anyway, I'm not going to go through that here. I think you can confirm and check what D is, but this is something that I promise you'll use quite a bit. Okay, so what are we going to do? So we have a few variables. We have two independent variables, x and t. We have one parameter that appears in our initial conditions, that's mu naught. And we have one parameter that kind of scales the spatial derivatives, and that's our flux, our diffusion parameter. So mathematically, what we're interested in is we would like to know how U is a function of all these parameters, a function of x, t, diffusion coefficient, and U naught. In this case, there's no magic, there's no like intuition, there's no nothing. We just looked at the equation and the initial and boundary conditions, and we just pulled all the parameters and variables out of there. Independent variable, and then parameter that applies in the initial conditions, and then our dependent variable that we're interested in. We wrote them down. We can do the same process we did before. We can say that U, the units of U must equal the units of x to the A, t to the B, d to the C, and U naught to the little d. Okay, we know the units on the left-hand side of my equation. It's going to be mass per volume. So the left-hand side should be something like mass per volume. We know the dimensions of all these parameters. We already figured them out. So we have length is to the A times to the B. D we just figured out. We said D was going to be length squared per time to the C. And initial concentration is the same. It's going to be mass per volume to the unknown quantity. I'm going fast. Any questions on this? This should just be hopefully following the way we approached this last class. I can collect all my variables, so it's a little bit less messy. And so I have L is going to be the A plus 2C numerator on diffusion coefficient, and then the denominator minus concentration, so it's minus 3D. T appears as B minus C, and mass appears only in D. All right. 3 equations, one for length, mass, and time, and 4 unknowns. We're going to have something that we will have to leave unresolved. So again, following the same procedure as last class, the equation for length says that A plus 2C minus 3D equals negative 3, because negative 3 is the exponent on length on the left-hand side of the equation. Time is just B minus C, and there's no time on the left-hand side of the equation, so that's got to equal 0. And mass equals just 1, so D is equal to 1. So clearly D is 1. We can solve, I'll just arbitrarily choose to solve for B and C in terms of A. So what does that mean? That means D is equal to 1, and B is equal to C, which is equal to negative A over 2. I'm going fast. You can check my algebra after class. Are there any questions in terms of what I'm doing? Just following the procedure we outlined last class. Here's where it gets interesting. So now we can go back to here. And we can just put in, so D is equal to 1, C is equal to negative A over 2, B is equal to negative A over 2, and X is equal to A. So we can come over here and collect all these things. And we can say that U should scale as U naught, which is to the 1 power, times X over the square root of dt to some unknown power, we'll call it A. So again, same approach as before. We can look at this in the same way. So this quantity is dimensional. If I divide U by U naught, I get a dimensionless quantity on the left-hand side, dimensionless quantity on the right-hand side. What's the difference between the dimensionless quantity on the right-hand side now than what we've had so far?
The square root of basic, what do they call it? Units of measure.
Okay, so you're picking up on the square. Oh, wait, so say that again. The last part, the units of measure. What do you mean?
Like time and time and length.
Yeah, exactly. So this is exactly right. So in this case, the dimensionless product that appears in our general solution for U contains both of the independent variables in our problem. The independent variables are x and t. Our dimensionless product contains both independent variables, x and t. That's a big deal. So this quantity here, I'm going to define a new quantity, call it eta, which is just going to be x over root dt. And this is what's known, eta is what's known as a similarity variable. Similarity variables occur whenever you have a dimensionless product, dimensionless group that contains the independent variables in your problem. We could have solved this problem a different way. I chose arbitrarily to leave A as the unknown. We could have picked a different one and arrived at a different write-up for this problem. Had we have chosen to keep A as the unknown, had we have chosen to keep, I think, B as the unknown, we would have gotten something that was a little bit flipped. We would have gotten that, we would have gotten like dt over x squared as our dimensionless quantity in there. I'll just say that in general, the two representations are completely equivalent. They can be transformed into each other. But this is a case where, because our equation that we're interested in over here is involving derivatives, it's going to be easier for us to take derivatives of the independent length parameter when it's in the numerator than when it's in the denominator. So in general, if you find a dimensionless product that contains your independent variables, check to make sure that the spatial dimension is in the numerator. It'll likely make your life easier for doing a calculation. It's not required, you can do it, it's just kind of a good rule to keep in the back of your mind. Having the spatial parameter in the numerator is typically more useful when dealing with similarity parameters. When you're reading papers, you'll see this occurring as well. Okay, so physically, what does this mean? I'm going to box this equation for us. This is important. So we have a similarity variable that we just found kind of just by looking at the dimensional analysis of this problem. And this implies that our concentration has a very specific dependence on the independent parameters in the problem, independent variables in the problem. This means, as we're going to see, that we're going to have self-similar behavior in this problem, in which kind of all of our results will be able to collapse on some self-similar curve. It also allows us to write our U, our concentration that we're trying to solve for, in terms of just one variable, eta, instead of x and t. This makes our problem that started as a partial differential equation, which is hard to solve, it now turns it into an ordinary differential equation because the only thing we need to take derivatives of are eta. We can just take U with respect to eta. Now we've gone from reducing our problem from a PDE to an ODE, and our ODE, as we'll see in a minute, is going to be pretty straightforward to solve. So as we'll see coming up, just by finding this parameter, we've significantly reduced the complexity of our problem. I'm going to pause here, give everyone like 2 minutes to hang out and regroup, and then we'll come back. And then if there's any questions, feel free to fire them at me, either in the chat or just out loud. Try to get my hand to stop being asleep. That's holding this thing. check the computer. To those at home, when I disappear, it's because I'm looking at the computer. So I'm actually like trying to see the chat room. So the computer is just in a weird spot. All right. Awesome. Thanks. Okay, cool. So there's a question in the chat for everyone in the room and anyone who's not reading, which was, how did we say that U is equal to mass per length cubed? That is given in the problem. So the concentration is usually either mass per volume or number per volume. And so in this particular problem, when we're looking at chemical concentration, the thing that we're interested in, U, is has the dimensions of mass per volume. So it's a concentration, and so that's essentially specified. So that's what we're looking to measure. And typically that's the case. You usually, when you set up a problem to do something with dimensional analysis, you usually have, what am I looking for? I know what it is in terms of what the quantity is. And then I have all the parameters in the problem that are going to need to match the dimensions of that quantity. So I just gave that the concentration, the dependent variable in this problem, has the units of mass per volume. Yeah.
So we took all the parameters we know about this problem, and what else can determine what A is? B, A for the dimensional group.
You mean the actual power of A?
Right.
Yeah, so what will determine it's actually a little bit more complicated than that, and I think you'll see it in a moment. So what this means is the concentration depends on the initial concentration and then some function of eta. That function could be polynomial, so A could be like 2, or it could be log, exponential, more complicated functions. And so we will now take this functional form, put it back in,
Okay.
and that's going to allow us to solve for it. In this particular case, we can solve for it exactly, and we'll end up knowing the functional form that eta appears, and that's what we'll do in a minute.
But it's not always the case.
So yeah, in the case of the drag on a sphere, the functional form for how f of pi depends on pi is extremely complex and nonlinear. It doesn't have, this is my best guess, my best sketch of what it looks like. It's like it drops linearly and then it's kind of plateaus and there's a really sharp dip at some Reynolds number. sometimes what you can do is figure out what that functional relationship is in certain regimes. So in fluid mechanics, you'll often kind of specify whether you're in the viscous regime or the inviscid regime or the high turbulence regime, and kind of isolate the function you're looking at and say, like, okay, in this regime it's constant, or in this regime it's linearly dependent. In this particular problem with concentration, we can solve it for analytically. Oftentimes what you can do is kind of combine the tools that we've talked about so far. So what you can do is kind of look in some intermediate regime, see how it behaves in that intermediate regime, maybe look in a different regime, and then try to stitch them together. So it's not true in general that you can solve for it, but oftentimes, and the point I'm trying to make here is that just getting it to this form allows us to simplify the problem to the point where we can solve it. Or it might allow us to simplify the problem to the point where we can't do an analytical solution, but maybe we can do more quick numerical calculations and stuff like that. So basically can reduce the complexity of the problem. In this case, it reduces it so much that we can kind of back of the envelope solve it.
Does it also allow you to do like experimentally, you can find different parameters of it?
Exactly, and that's the example we gave with the drag on a sphere. Is you can just you kind of know what you're looking for now. You know what you need to vary, and you know what you need to measure, because you can just take, you can essentially vary that parameter and see how whatever it is you're looking for, the dimensionless drag or the dimensionless concentration changes. And so it can be an instructive way to tell you how do you conduct the experiments, as opposed to when you have so many parameters, it can be like a shot in the dark. All right. So we know that this is not the most general form that we can write this. We know that it could lead to kind of additive combinations of eta or various constants. But we know that we can take this thing and write it as u equals u naught times some unknown function of eta. It looks like a subtle difference, but it kind of removes that assumed polynomial dependency on eta, where we're just saying, oh, it's probably just some exponent. It's now saying, well, this solution, for it to be completely general, could have a constant here and a power plus another constant times this and this quantity to a different power just forever. And so we can just say, in general, we expect it to be some function of eta. The reason why this is kind of important is because now we have an exact relationship for u that we can insert back into our differential equation, which is this thing here. That's pretty straightforward, but it does require us to recall the chain rule. The chain rule, if you remember, you take the derivative of the outer function with respect to the inner function, multiply that by the derivative of the inner function with respect to the independent variable. For those of you who find it not helpful to hear that in words, the chain rule is telling us that if I need to take the derivative with respect to, if I need to take the derivative with respect to time of f of eta, I need to take the derivative of the outer function with respect to the inner function. So take the partial derivative of f of eta with respect to eta, and then multiply that by the partial derivative of eta with respect to the independent variable. So I know this might be a little bit tedious, but I'm going to just do it out so that everyone's on the same page. So using the chain rule, we can say, all right, I have my equation D. So du dt would be equal to u naught times f prime of eta times d eta dt. So a note on the notation I'm using, I used comma to describe a partial derivative, and I'm using an apostrophe to denote ordinary derivative. F only depends on eta, so taking a derivative with respect to eta is an ordinary derivative, and so we have f prime of eta. We don't know what f is, so we just know that the derivative is going to appear. But we do know what eta is, so we can take the time derivative of eta. It's a little bit of pain, but that's okay. So this quantity, actually, let's change that color. This quantity, I'm looking at partial derivative of this awful thing, x root dt by time, which is equal to negative x over 2d to the 1/2 time to the 3/2. All right. I can write this a different way, which is to say that, let's come back over here. It's equal to u naught f prime of eta times eta over 2t. So this is eta, and then I have an extra time in the denominator, and a 2 in the denominator. Okay, so that's the right-hand side of my diffusion equation. I got to do this again for the left-hand side. Let's pick a different color. Let's go over here. So there we go. So what am I doing here? I'm going to take two derivatives. So I'll take u naught f double prime of eta times two derivatives of eta with respect to x. That one's a little more straightforward. And I'm left with just 1 over dt. Okay, so now I have everything I need. I have the right-hand side of the equation, part of the left-hand side of the equation. I just need to multiply this by d, and I can stitch this all together. Sorry, okay. So stitching this all together, I get, let me just kind of write this out in a more tedious way. Okay, so I get a d times the left-hand side term, which is u naught f double prime of eta 1 over dt is equal to negative u. Did I not put a negative?
Yeah, I think you missed a negative.
I missed a negative, huh, didn't I? Oh, wait.
There should be a
Here.
negative in eta, there should be a negative.
Yeah, right here, thank you. So the derivative led to, yeah, perfect. Thank you. The negative here, because we're taking derivatives for times on the denominator, so I lost the negative there. Is equal to negative u naught f prime of eta, and then it's eta over 2t. And you can already see that this is going to work out quite nicely for us. The d's are going to cancel out, the t's are going to cancel out, the naughts are going to cancel out, and I'm left with a much simpler equation. Which is that f double prime is equal to negative 1/2 eta f prime. Now we also have to take care of our boundary and our initial conditions. This is, I think, often a little bit strange because we started out needing 3, and now we only need 2 because we only have a second order ODE. And what ends up happening is that if you notice in our initial conditions, 2 of them are occurring at 0. And so because of that, when we have this similarity variable, those conditions are identical. And so then we're left with kind of 2 conditions, one that's corresponding to what's happening kind of at time and space is equal to 0, and one that's happening at kind of infinite time and space. So we end up starting with 3, and now we're down to 2, and we are going to do the same kind of inserting u into the initial and boundary conditions, and it's pretty straightforward. What you end up with is that f of 0 has to equal 1. That doesn't look like a 1. And f at infinity has to equal 0. Why 1? 1 is corresponding to basically the fact that we're normalizing our concentration by the initial concentration. So we're trying to start at 1. And so this doesn't seem like a big deal, but it kind of is. We started with a second order PDE. All we did was look at the dimensions, and then we reduced that to a second order ODE. And if you know anything about differential equations, you know that this thing is fairly straightforward to solve. I will go through the solution. I will say, and this is in the notes that I typed up as well, this is not a class on differential equations. I don't need you to kind of off the top of your head remember variable substitutions and such. The point of this is to say, with a few lines on pen and paper and a recognition of common functions, that we can very quickly solve this. So I'm going to show that to you, but in a way, getting to here is the point that I want you to be able to get to. Once you get to here, there's a million ways you can solve this. I will honestly tell you, I never do it by hand. I just do everything in Mathematica. This thing's pretty straightforward doing Mathematica. I think I even put the code in the notes if you want to do this in Mathematica, because it ends up with a bit of a messy set of functions. The way you would solve this problem, so I'm just going to put this in a different color just to say this is not really vitally important. The way you would solve this problem is by making a variable substitution. And so you would say, let G equal f prime. You should probably like dust the cobwebs off of some differential equations class you took forever ago. So if we let G equals f prime, then our new equation becomes G prime equals -1/2 eta G. This is nice, it's the first order ODE. This has a very general and well-known solution, which is that G is equal to some constant, alpha, times e to the negative eta squared over 4. So this is G. We actually need F, so we need to put it back in, and we're going to have to integrate it to go from G to F. So this means that we would say that F of eta is equal to some other constant, because we have to integrate here, plus alpha, which is a constant, times the integral from 0 to eta of e to some fake variable that we're substituting in here. We're going to integrate over s, we'll call it. That's the wrong parentheses. Okay, we have f. We have some awfulness over here, but if we put in our known boundary conditions, we know that f at 0 has to equal 1. So that makes life easy. That means beta has to equal 1. And f at infinity has to equal 0. That means zero to eta is equal to infinity. My alphas and my infinities look similar, sorry about that. E to the same thing, minus s squared over 4 ds. This quantity has to equal 0. As it turns out, which who knew, I didn't know this, this quantity integrates directly. Yeah, to root pi. Yeah. And so now we're, again, if you're kind of lost right now, that's okay. This is more mainly for sport. Now we're able to write that f of eta equals 1 minus 1 over pi as the integral from 0 to eta of e to the negative s squared over 4 ds. And as it turns out, again, that this thing has a nice functional form.
Fresnel integral?
Fresnel integral, I think of this as the complementary, it's the complementary error function, because we're taking 1 minus the error function. So this is like 1 minus the error function. And so therefore, our solution is that the concentration is going to be equal to our initial concentration times the complementary error function of eta. So,
I'm sorry, what was the question? I didn't hear it very clearly.
yeah, I'm sorry, I'll repeat it. So one of the students in class was guessing whether or not this integral here was the Fresnel integral or the error function, and it turns out it's the this quantity that I underlined is the error function.
Mm-hmm.
So E is that E ERF of eta, but since we're taking 1 minus ERF, we end up with the complementary error function, so it's E ERF C.
Mm-hmm.
It doesn't matter. If you type in, just like you would go to Mathematica and type in plot sine of x, you can type in and plot error function of x or plot complementary error function of x, and I'll show you what it looks like. It looks like this. So let me tell you the answer first. So putting all this together, we would find that U of x and t is equal to U naught times the complementary error function of eta. And since we want to put this back in terms of x and t, we can say that this is complementary error function of x over 2 root dt. And if you don't understand or don't follow directly what I did here, that's totally fine. If you want to, load up the notes that I have on the website, and you can start, I have code in there where you can start playing with this in Mathematica, and you can see like, oh, this integral equals that, and therefore if I need to apply this initial condition or boundary condition, I can determine the constants. I step through it so that you can see. What I think I will do, I'm definitely going to do this more as we get more involved with Mathematica. But maybe I'll try to do this now is, maybe I'll put like Mathematica notebooks that go along with the sections or chapters that I'm typing up on the website as well, so you can just kind of click go and it'll spit this thing out. So I guess my takeaway is if going from here, if going from here to here is not straightforward, that's okay. Go read up on what I've written up about this. It's also not really the point of this course. The point of this course is to go from here, which is a complicated partial differential equation, use dimensional analysis to find a similarity variable, then use that similarity variable to reduce our PDE to a set of ODEs that can be solved. Doesn't mean it's straightforward to solve. It doesn't mean it's straightforward for you, and that's totally fine. It wasn't straightforward for me the first time I did it. What does this thing look like? What does the complementary error function look like? Maybe that's the more interesting thing, and let me show you what that looks like. So if we plot u as a function of eta, you end up with something that, I want to do this. I'll do this a little differently. We'll call this 0, this 5, this -5. You end up with something that looks like this. Basically, kind of plateaus, drops, and then plateaus again. The way to think about what this plot means physically is to go back to what our kind of imagined data is. I'm going to grab this thing, paste it over here. And what this is saying is that all of these curves that are sketched out over here, in which we kind of have something that's starting at u naught, dropping to 0. Then maybe it goes for u naught longer, drops to 0. If I rescaled, so right now I'm plotting as u as a function of x, but I'm plotting for different t's. Instead of doing that, where I have a plot of u as a function of x for various different times, I can rescale my plot and combine space and time together. And then all of these lines would either get stretched or compressed and fall on that one complementary error function curve. So if I had data for the concentration at various points in time, I could plot it u as a function of x, and I would get all these little nice little curves here. Or I could plot that data as u as a function of eta, and all of my data would sit here. Oh God, that's huge. Wow. Let's try that over. Let's try this. All of my data would sit like on this line for various times and spatial intervals. They would all collapse. And so what we're finding, the self-similar behavior here, is the fact that my curve, which is saying what the concentration is doing in space at various times, all of those space and time curves will collapse onto one kind of universal space and time curve if I scale my variables properly. How would I know to scale my variables properly? I just started with the initial problem, which is this system of a partial differential equation and 3 boundary or initial conditions. Identify the independent variables, identify the parameters in the problem, and identify the dependent variable that we're solving for. Dimensional analysis led to us finding a dimensionless product, and then it takes the wherewithal to say, hey, our dimensionless product contains all the independent variables in the problem. That's a special thing. Okay, I can rename that combination of things, in this case, eta, and by doing so and inserting this general solution back into my initial differential equation and initial conditions, I arrive at an ordinary differential equation that is significantly easier to solve. And in this case, I can solve it analytically just by kind of writing everything down. So our solutions can be represented by a single function. Sometimes it's a curve, sometimes this is a surface, depending on if we're in a more complex system. A natural question might be, when do similarity variables occur? When might you expect to find a similarity variable? I think this answer might be a little unsatisfying in the moment, but we're going to talk a lot about these terms that I'm going to use here in the next week or two. But typically, these self-similar variables and these self-similar solutions occur when the problem you're studying lacks a characteristic spatial or time scale. So here's a problem where we're starting at time is equal to 0. It can go on for an infinite amount of time. And we're looking at a spatial domain that starts at 0 and can go on for an infinite amount of time. I'm sorry, an infinite amount of space. So there's no obvious length or time scale that we would expect something to behave on. So what's an example of something where we would expect it to have a characteristic scale? You might take a sheet of paper, which I don't have, and kind of hang it off the edge of a table. So imagine you take a sheet of your notebook paper and hang it off the edge of your table. You have a length scale there, which is the length that's hanging off the edge of the table. It's finite. And you'll notice that 2 behaviors occur. When you hang your sheet of paper off the edge of the table, a small amount, the sheet stays flat. If you hang the sheet or a really large amount overhanging the edge of the table, the sheet bends a lot. And so there's a length scale there in which the behavior switches from staying flat to sagging off the end of your table. That's a problem where there's a characteristic length scale. There's probably some length scale that says, well, once I get beyond this value, something different happens. That would be a characteristic length scale in that problem. We will talk about how to find these characteristic lengths and time scales coming up. But this is a problem where, like, when you're dealing with this infinite spatial and temporal domain, there's not an obvious length scale that is relevant to us. There's not an obvious time scale that's relevant. And we could say that maybe there's a characteristic diffusion time, but we then would have to say, well, a characteristic time for what to happen, for it to diffuse over what length. So typically, if you have a problem that is lacking a characteristic scale of some sort, there's often going to be some self-similar analysis or self-similar variable that will occur in this intermediate regime. I don't know if the concept of self-similar is confusing or it makes sense, but basically that concept of self-similar, we talked about that physical similarity where the crack looks the same, or the drag behaves the same as long as we scale up everything accordingly. This self-similar behavior is a way of saying, like, we can collapse all of these curves onto one curve if we are plotting our things appropriately, if we find the right way to rescale our spatial or time domains. And if we do so in such a way that they fall upon each other, that's what's referred to as a self-similar behavior. Questions? I've gone really fast, and so I fully expect that there would be some confusion. So let me know. Throw things at me. I'll monitor the chat as well. Because this is all I wanted to cover today, so I want to just make sure that we're on the same page here. For those of you who've done anything with dimensional analysis before, you've probably encountered the Buckingham pi theorem. I'll talk about that next class, mainly so that you have a formal way of thinking about these things. I will probably repeat this next class too. Like, I never start with the Buckingham pi theorem to like do a problem that I'm interested in on my own. However, it can be a useful way to conceptualize it, and it can help give us some guidelines to determine when can we ignore a dimensionless product? When can we, what happens if we ignore a dimensionless product and that was a bad decision? So I'll give an example of what happens in that scenario next class. And so I will go, if you're familiar with this and being like, why is he not talking about Buckingham pi? I'm going to do that next class. I find it to be more useful after you've seen some examples, just to kind of put everything into a general framework. And so we will talk about that. No questions? Nothing? This is okay?
I have a question about setting the boundary condition for the new capital F function F. So when like F is really small, but like finite but small, but when T is like really going to the zero, like to the limit.
Mm-hmm. Oh, okay. So you're talking about how you're going to have, you have one variable in eta that is going linearly and one that's kind of diverging more slowly because you have the square root property. Yeah, that's a good question. So I don't think it changes the boundary or initial conditions. I think what it might do is, because those conditions are happening at exactly time zero, I have to think about how the system behaves kind of like in the limit of, or like asymptotically approaching it from, as asymptotically approaching t is equal to 0 at a finite x. I don't have a good answer for you in terms of kind of how to conceptualize that. We will talk a little bit later in the class about kind of ideas of dominant balance, which is looking at how solutions change as different variables go to 0 or infinity at different rates. For this particular problem, I don't know what would change about that. Yeah, I have to think about it. I don't have a good answer for you in the moment, but I'll try to think about what that would look like. I don't think it affects the boundary conditions. I think it could affect the behavior, like kind of near eta is equal to 0, but I have to think about that. It's a good question. Yeah. All right, if there's nothing else, thanks everyone. I will try to get these things posted as soon as I can. And I'll see you all on Thursday. Thanks everyone.